Hi, today we're going to be looking at topic 4 for chapter 14, which is about some probability rules. So we looked at doing probability, particularly using combinations the other day. Now we're going to look at some special probability rules that will help us with some other types of questions. Okay. First, I'd like to define for you what a mutually exclusive event is. So mutually exclusive events are events that cannot occur at the same time. So for example, like if you're dealing with a deck of cards, like getting an 8 versus getting a jack. When you pull out of a deck of cards, you can't get a card that's both an 8 and a jack at the same time, okay? As far as your like status at the high school, you can be considered either a junior or a senior, okay? Like on my roster, you're not listed as both, even if you're missing credits. You're either listed as a junior or as a senior. In a sports context, we could say something like exactly 3 outfielders versus, for example, maybe like in a little kids league, exactly 4 outfielders. Okay. And so if we have events that are like, so those can't occur at the same time. Okay. You either have 3 or you have 4. You can't have 3 and 4 at the same time. All right. So if events A and B are mutually exclusive, then that means that the probability of A or B happening, as we looked at before, is the probability of A happening plus the probability of B happening. So as long as events are mutually exclusive, we can define the mutually exclusive events in that fashion. As if the probability of A or B, we just add those together, okay? Now, complementary events are really like a subset of mutually exclusive events, but they're even more special, okay? Now, in a deck of cards, it's true that you can't do an 8 and a jack at the same time, but those events aren't complementary because there are cards other than 8s and jacks. So complementary events are when the events cover all of the outcomes. So complementary events are mutually exclusive events, but they're mutually exclusive events that will cover everything. So in a deck of cards, if we wanted to think about 2 situations that couldn't happen at the same time but cover everything, we could say red cards versus the black cards. Each card is either a red, a heart or a diamond, or a black, a spade or a club. You can't have one at the same time, and those cover all of the possibilities. Another possibility is like if we think about dice, for example, or like I should say a die, it's a pair of a dice, is if we have an even or an odd outcome. You're either going to roll a 1, 2, 3, 4, 5, or 6 on a regular die. So your outcome is either going to be even or odd. It can't be one at the same time. And that covers all the possibilities. So what would be complementary to winning 10 games? Is there a way to describe not winning 10 games other than saying not winning 10 games? And some people could say, well, winning no games. Well, yeah, but couldn't you win 1 game or 2 games or 3 games? There are a lot of different possibilities. So sometimes just putting a not in front of it is the only way for us to get that these events are complementary. I know it seems a little shady, but that's sometimes what happens, okay? So because these events are covering all the possibilities, it's important to note is that the probability of complements always adds to 1. okay? Because either this is going to happen or that's going to happen for a total of a probability of 100% or 1. So that means, and this is a little notation the text uses that I haven't seen before, but they say if events A and then AC, so the complementary event, if those are complements of each other, then if you want to find the probability of one event occurring, what we could do is we could take 1 minus the probability of its complement. So that's all that means, is that to find a complement, the probability of a complement, we take 1 minus the other one. All right. So let's look at these examples and see if we can use what we've just learned to answer them. Example 1 says, let event A be that a student receives an A in statistical reasoning. Give an example of an event that is mutually exclusive to event A. So that means that it can't happen at the same time. Well, what's different than getting an A? Well, one idea is if the student receives a B in statistical reasoning. Okay? So those are mutually exclusive events. You can't get an A and a B at the same time. It has to be one or the other. Of course, there are other possibilities, right? You could receive a C, receive a D. Let's try not to receive an E, okay? Or a D either. All right, example 2. Let event A be that a player plays third base in baseball. Give an example of an event that is complementary to event A. So complementary means that it doesn't overlap and it covers all the possibilities, but there's not a name for something that's not third base. You know what I mean? So I guess what we would have to do is say that the complementary event would be that a player does not play third base in baseball. Now, if there were a special name for players that don't play third base, of course, we'd want to use that. But that is one way when you're kind of stuck. That's one way that we can always find a complement. Okay. So let's also look at independent events. Events are independent, and we talked about this in the past, if knowing the outcome of one event, so one event does not change the probability of the other event occurring. So does not change the other event. So one thing happening isn't going to affect the other, essentially. And if two events, A and B, are independent, then the probability of A and B, we're going to take by the probability of A occurring times the probability of B occurring. And we've done that idea with different combinations of events, and now we can do that with probabilities as well. So how could we use this idea of independence and probability? Suppose that a basketball player has the ability to make 55% of his free throws. Assuming outcomes of the free throws are independent, what's the probability that he takes 4 free throws and misses all of them? All right. Well, they're saying that the ability to, that his ability is to make 55% of his free throws. What that's telling us is that the probability of a make is 55%, or 0.55. Now, it's asking us what's the probability that he takes 4 free throws and he misses all of them. So what that means is that we're going to have a miss, a miss, a miss, another miss. It's like I'm playing, okay? Now, is it a miss or a miss or a miss or a miss? Or is it a miss and another miss and another miss? Hopefully you're seeing that this is going to be and. So what that means is that we're going to be multiplying these probabilities together. The thing is that they told us the probability of a make, and they didn't tell us the probability of a miss. But let's think about that. If we want to find the probability of a miss, what's special about make and miss? Well, make and miss are events that can't occur at the same time, so they're mutually exclusive. But even more special is that those are the only two options. You either make it or you miss it. So that means that these are complements. And because they're complements, to find the probability of a miss, we could take 1 minus the probability of a make. So that means that the probability of a miss is 0.45. So the probability of this first miss is 0.45. Now, because the outcomes are independent, that means that the probability of missing a second time is not affected by the first, which means that the probability is the same, 0.45. And then it follows that that's the same for the third shot and the fourth shot. So 4 free throws, all misses. So we want to put this in the calculator, but before we do that, what's a better way for us to write 0.45 times itself 4 times? Well, this brings us back to the idea of exponents. And this is the same as 0.45 raised to the 4th power. Remember, exponents are when you multiply something by itself. So we would want to use an exponent of 4. So let's do that here. Let's take 0.45 and raise it to the 4th power. And we've been rounding our probabilities to the nearest, to the nearest thousandth. So that's going to be 0.041. And as a percent, we would move the decimal over 2 places. So that's the same as 4.1%. Another thing we did in a previous lesson is talk about interpreting the probability. Now, last time we had a numerator and denominator, but let's look at what this question is really asking about. And the last part of the example 3 tells us that. It's saying what's the probability that he takes 4 free throws. So that's what's happening overall. That would have been like our denominator type of a thing. And then we want to know that how likely it is that he misses all of them. So this takes 4 free throws is like our denominator, and misses all of them is like our numerator. So we could say something like, if this player takes 4 free throws repeatedly, so that's what would be happening over and over and over again. This number represents the likelihood that he's going to miss all of them. So I'll say he'd miss all 4 about 4.1% of the time. And that's all we have to do to interpret that probability, okay? Let's continue using these ideas of the mutually exclusive and particularly complementary events going forward. Let's suppose that a volleyball player, the probability that a volleyball player makes her next serve inbounds is 88%. Let's once again assume the outcomes of the serves are independent, and let's find each of the following. So the fact that we're saying the probability that she makes her next serve inbounds is 88% means that in this question, we're going to say that the probability of a make is 0.88. So we want the probability that she makes her next 2 serves. So that means that we want a make and a make. Do we know the probability of a make? We do. It's 0.88. So that's going to be 0.88 times 0.88. And again, we only do this twice because we're just looking at her taking 2 serves. And so that's the same as 0.88 squared. And if I take 0.88 squared, this is nice, but if we are practicing rounding to the nearest thousandth, that would just be 0.774. or 77.4%. Okay, so we were able to use that information in example 4A. Now, example 4B asks us to find the probability that she makes her next serve inbounds and then misses the next 2 serves. So we want a make, miss, and then a miss. They were very particular about the way that that happened. And then this is not making or missing. This is making and missing again. So we know the probability of a make was 0.88. But what about the probability of a miss? Well, lucky us, make and miss are complements. So we can say that the probability of a miss is going to be 1 minus that 0.88, which will be 0.12. So that means the probability of this miss is 0.12. The probability of that miss is 0.12, and then we can multiply. Again, these probabilities don't change because these are independent values. So we could take, let's just look that if we were to use exponents, we only have 0.88 once, and we have 0.12 twice. So we could take 0.88 times 0.12 squared, and that gives me about 0.013, or about 1.3%. Okay? So letter C. If she takes 3 serves, find the probability that she misses 2 of the 3 serves. Now we might say, oh, well, we found that here. She's missing the 2 of the 3 serves. But that's what happens if she makes, misses, and misses. Are there other ways for her to miss 2 but make 1? I mean, she could miss the first 2 and then make 1. She could also miss the first one and miss the last one, but make the middle one. And those are different ways that that could happen. So in this case, I have 0.88 times 0.12 times 0.12. This second way, I have a miss, which is 0.12, a miss, 0.12, times a make, 0.88. And then the last one, I have a miss, 0.12, a make, 0.88, and then a miss, 0.12. Now, when we're thinking about these different scenarios, could this and this and this all happen at the same time? No. She's either going to make the first one, or make the third one, or make the second one. So there is an or between those possibilities, which means that between all of these 3 possibilities that we want to add. Now let's look at those possibilities. They look like they're a little bit different, but do you see that each of the examples or each of the scenarios has 1.88 and 2.12s? It's the third one. So there are 3 that are the same. Now, if we were multiplying, we would raise to the third, if we're multiplying 3 of the same things. But here we are adding 3 of the same things together. So we do have 0.88 to the first. We don't need the 1, I'm just being dramatic. And then 0.12 squared. And think about it. What if you had x plus x plus x? Doesn't that give you 3x? So if we have this plus this plus this, that gives us 3 thises. So what that means is that we're going to have 3 of those, since there are 3 ways for that to occur. And so then we could just say 3 times 0.88 times 0.12 squared, and that gives us 0.038-ish. Or if I move the decimal over, that gives us about 3.8%. Now, the last thing we'll look at is this idea of the complement rule in a special scenario. This idea of at least one success and no successes, those are complementary. So when we want to find the probability of at least one of something happening, we need to realize that at least one and none are always complementary. That's like a real important thing. This idea that the probability of at least one, whether it be at least one success, failure, or whatever, but at least one is equivalent to 1 minus the probability of none. And so if we're talking about successes, that means that the probability of at least one success would be 1 minus the probability of no successes. So let's use this idea. I'll just highlight this again here and here, okay. Let's use that for letter D. It says if she takes 3 serves, find the probability that she makes at least one of the serves. So let's use that. The idea that the probability of making at least one is going to be 1 minus the minus the probability of making none, because they're complements, okay? So let's think about what making none means. So to make none, the probability of making none would mean that she doesn't make, so she misses, and she misses again, and she misses again. Now, this is still the same question that we've been dealing with in example 4. We said that the probability of a miss was 0.12. And because we're multiplying that by itself 3 times, that's like 0.12 to the 3rd power. So let's put that in here. This idea that the probability of making none is going to be 0.12 to the 3rd power. And so then to make at least one, we would just take 1 minus this value. So I could take 1 minus 0.12 to the 3rd power, and that gives me about 0.998. Or about 99.8%. So this is really important when you see problems that say at least one. This is the model that you're going to want to follow for those type of questions. Okay. So let's use what we did in example 4, as well as the definitions that we talked about on the front, as far as mutually exclusive, complementary, and the independent values. And I'd like you to try this you-try question. A basketball player is a 70% free throw shooter and takes 3 free throws. And see if we can answer these questions. I am going to answer the first one with you because I don't want you to sit tight on letter A. It says, do you think the outcome of each free throw is independent? And then explain. We usually assume independence. Back when we talked about the hot hand in sports, we always assumed that that one outcome was not going to affect the other. So we always kind of assume independence. And so here I'm going to say yes. We assume independence. And also we'll say one outcome shouldn't change the probability of the next. So if we write our answer that way, then we talk about the idea of assuming independence, but also the idea of what it means to be independent, that one outcome doesn't change the probability of the next. So again, see if you can use what we did in our questions in example 4 to see if you can answer B, C, and D, and then flip back to the other side to see about about letter E. Okay, I'll give you guys a minute to do that. Okay, let's see how you did. In letter B, it wanted the probability that she makes the first 2 shots and misses the last one. Well, we needed to see here that the probability of a make was going to be 70% or 0.70, and therefore its complement, the probability of a miss, is going to be 1 minus 0.7, which is 0.30. So that means that we're going to want make, miss. So 0.7 times 0.7 times 0.3, which equals 0.70 squared times 0.30, and that gives me 1.47 or 14.7%. The next question wanted the probability that she makes any 2 of the 3 shots. When we have any 2 of the 3 shots, this is where we have to think about all the different possibilities. We could make, miss, miss, make. And there were 3 different ways that happened. That's where that 3 is from. Excuse me. And so then we're each of these has 2 makes, which is 0.7 squared, and 1 miss, 0.3. And if we multiply this together, we end up with 0.441 or 44.1%. Okay. Next, it wants the probability that she makes at least 1 shot. Well, this is where we go back up to the idea that the probability of making at least 1 is the complement of making none. So we'll use that. Making none does mean missing them all. And so that means that we'll have miss and miss and miss. 3 misses would be 0.3 to the third. Sorry. And we'll subtract that from 1 to get 0.973 or 97.3%. And then lastly, if event A is she makes 3 shots, what event could be the complement of event A? Well, is there something that means doesn't make 3 shots? There isn't. So this should be our correct answer. The only thing we could really say is she does not make 3 shots. Now let me show you a popular wrong answer because I don't want you to give it, okay? I see a lot of, oh, she misses 3 shots. Those are not complements. I know that make and miss are complements, but making 3 shots and missing 3 shots are not complements. Think about it. We have make, miss, miss. Are those the only 2 possibilities that exist? No. We could make, miss, miss. We could miss, make. I mean, there are lots of different things that can happen. So she misses 3 shots is not a complement. So just keep that in mind going forward. Okay, have a great day, guys.